All right, next I'd like to look at another two-body problem. And in this one, we'll call it the Atwood machine problem. We have two masses that are hanging from what we'll call now a frictionless massless pulley. And so that's kind of an idealized concept in which the friction is small and the mass is small relative to the other masses in the problem. And not to worry, we will teach you how to work with pulleys later that have mass and friction. But for the moment, let's just say that it has no friction or mass. And that big M is bigger than little m. So big M, let's say, is equal to 2 kilograms, and little m is equal to 1 kilogram. So that you have a pretty good idea which way this system is going to go under the influence of gravity and a stationary pulley, which is being held in place there by this nail. And so for this problem, let's find the acceleration of m1 and m2. Or big M and little m, as I've labeled them here. Okay, so how do we do this problem? Well, in much the same ways we did that other two-body problem that we looked at recently, we'll identify the forces acting on each mass. But in this case, it's a cord that is connecting the masses together. So that's our direct contact force, is this cord. And that cord, because of Newton's third law, is going to have the same tension here as it does here, unless the cord has mass. And so we're actually a third idealization here. Frictionless massless pulley, also massless cord. Because if the cord has a little bit of mass, then the weight of the cord is also going to add, depending on the positions of big M and little m. Okay, and so, but these masses have no intelligence. They don't know. This one doesn't know that that mass is there. All it knows about that can directly affect it is the tension. Now the tension always points away from the mass in the direction of the cord. Okay, so that tension is going to be pulling up, but then pulling down, you're going to have an even bigger force equal to big mg. Now how do I know that this force is bigger than the tension? Well, because I know that this mass is going to be accelerating in the down direction because it has more weight than this one. So I know the system's going to be going this way. I know it's going to be picking up speed too, because it's an imbalance in forces. So therefore, mg must be bigger than the resistive force in which this mass is pulling along m1 for the ride. Okay, so then this little mass, little m, is going to have an equal tension here because of Newton's third law. This is the force of little m, big M on little m. Here's the force of little m on big M, is this tension. But we know that that tension has to be bigger than the weight, which is little mg. So I won't necessarily mark you off if you don't draw the force vectors having the appropriate lengths. But it is really important for you to see conceptually that this is what's creating the imbalance in forces that's making little m go up and big M go down. Now since big M is going down, and that's the direction of motion, I'm going to call that the positive direction for big M. So in the same problem here, I'm going to have two different positive directions. I'm going to have a positive direction that's up for little m and down for big M. Now the other option is that you could define up always as positive, but then you're going to get two different accelerations because this acceleration is going to be down and that one will be up. And so you have to come with A1 and A2. And then you have to say, well, they must be equal and opposite to each other. So that gives you a third equation. Makes it, I think, kind of confusing. And so even though it may seem confusing to make two positive directions, different in the same problem, I think it's the least confusing of the options that we have available to us. Okay, and if you start getting used to it, choosing the positive direction to be the direction of motion, it always works for you, and it always makes life easier for you. So we might as well get used to it sooner rather than later. Okay, so it's up to you. You can do it the other way if you want, but I don't recommend it. So for big M, our forces here are going to be big mg, because that's the positive direction, minus the tension equals big M A. For little m, this is the positive direction. T is bigger than little mg, so we can write this as T minus little mg equals little m A. Okay? And by choosing the positive direction to be the direction of motion, you have now algebra to do here. All you really need to do is just add these equations together. So that is algebra, technically, but it's the easiest kind of algebra that you can do. And so if I just add the equations together, that gives me, the t's are going to cancel. So we get big M G minus little m G equals big M A plus little m A. Or factoring out a G on the left and an A on the right, we get big M minus little m G equals little m plus big M times A. So this gives us our final result, that the acceleration is equal to the difference in masses divided by the sum times the acceleration due to gravity. Okay, now, what I like to do with an equation like this is check it in limiting conditions, just to see if it makes sense. First of all, I know that if the system is balanced and the two masses are equal, then the acceleration should be 0. So that's the case if big M and little m are equal to each other. In the other case, let's say that big M is super big in relationship to little m. Okay, so the little m is like the mass of a proton or just something really, really small. Well, then what we have essentially is no mass on this side and all the masses on that side. So this side should be in free fall if this has no mass, right? So if little m, and the limit as little m goes to 0, acceleration just becomes big M over big M times g, or it's in free fall. So that matches up then in the limiting conditions. Let's see what happens in this example where big M is 2 and little m is 1. Then the acceleration is going to be 2 kilograms minus 1 kilogram divided by 2 kilograms plus 1 kilogram times 10 meters per second squared. Or that would be 1/3 g, or 1/3 times 10 meters per second squared. So the acceleration then would be 3.33 meters per second squared. All right, so that's 1/3 the acceleration due to gravity if these masses have a 2-to-1 ratio. Okay, and so without any pulley mass, essentially what's happening here is this is kind of like a tug of war where the pulley is just changing the directions of these forces from being ones that are out here pulling against each other to like this. But the equations are basically the same as they would be in a tug of war where little m was only pulling half as hard as big M was. Okay. And so now, if we wanted to, we could find the tension. How would we find the tension? Well, we could go to either one of these original equations and plug in for the tension. So if I use equation 2 here, then we'd have T is equal to MA plus MG, or little m times A plus G. So the tension then would be equal to little m, which is 1 kilogram, times A, which is 3.33 meters per second squared, plus 10 meters per second squared. So that would be equal to 13.3 newtons. Okay, so that then is, that's kind of analogous to what we solved for in that first problem that looked like this, where we had two masses and a force acting that way. The contact force is analogous to here, what we see are the tensions in the string. And so that's what couples the two masses together. All right, in the next example, I'd like to go back to a single body problem that I'd like to apply it to an inclined plane. Let's make this angle 30 degrees. And let's have a mass sliding down a frictionless inclined plane. Let's find the acceleration with no friction. Okay, so the question then that we're asking ourselves is, how fast is this thing going to slide? And so what we could do then is, first of all, draw all of the forces that are acting. So here we've got mg, that's acting down, so this is our mass m. We have the normal force, but that's not vertical anymore, because by definition the normal force is perpendicular to the surface. That's what normal means. Okay, and so in this case, because the surface is inclined, the normal force has to be perpendicular to that surface. And so that's how hard the surfaces are being pushed together, which we'll need later when we get to friction. Okay, so, but now the question is, what is the acceleration of the plane? And let's also find the normal force, because that might be fun to find, just in case we wanted to, later on, do this problem with friction. Okay, so here, I'm going to set up a coordinate system, but I'm going to define the coordinate system, and I hope this doesn't cause any of you bad dreams tonight. I'm going to put it along the surface of the incline, and not my regular xy coordinate system. You just go, oh, please, I was just getting used to that. So why are you turning the coordinate system along that way? And the answer is because there's no acceleration in the y direction if I choose this way. Can you see that? But if I choose this as my xy coordinate system, there's acceleration in x and y. It's going to be hard to separate them out, and it's going to be confusing. Even if you know what you're doing, it's going to be confusing. So just the correct choice of a coordinate system can greatly simplify the problem. But what that requires you to do now is to break up components, your vectors, into components that are aligned with your coordinate system. So that's what you always must do. Once you choose a coordinate system, you must then decompose your vectors into components that point in those directions. And so has this been accomplished already? Well, the normal force is already pointed in the y direction, so I don't have to do anything with that. But mg is a different story. mg is going to have two components, one that is in the negative y direction and one that is in the positive x direction. Okay? And so I could call this fx, this fy here. And so what we need then is this angle theta in order to get mg written in fy and fx written in terms of mg. Easiest way to do that is to look at this triangle here. If you look at this triangle, this is a 60-degree angle, so that must be a 30-degree angle, because this angle is also 90. And so that, although it's easy enough for me to see that right now, that may not be, if you don't look at it the right way on, say, an exam or something, you might get those mixed up. And so I think it's probably better for these kind of problems just to remember that that angle is the same as that angle and not try to prove it every time. You know, proving it once is enough. All right, so here, Fy is going to be mg times the cosine of 30. And that's a negative, right? Because it's pointed in the negative direction. And Fx, which goes along the surface of the incline, that's going to be mg sine 30 in this case. Okay, and so that's also the same fx that I could put up here so that it goes right through the mass. Remember that vectors, you can draw them and put them anywhere you want. They're still the same vector. But here I think it's more instructive for us to take this vector that I used in this triangle and place it at the point where it's actually acting, which is right at the center of the mass of the object. Okay, so this is the only x force that's acting, and the y forces are going to cancel. So you've seen this before. The sum of the y forces is 0. So that gives us F normal minus mg cosine 30 equals 0, or F normal equals mg cosine 30. Okay. Now in general, if this angle is theta, this could be any angle of inclination. We could call it cosine of theta. So what if theta is 0? Theta is 0, then we just have a horizontal level surface. And if that's the case, then the normal force is mg times the cosine of 0, which is just mg. The cosine of 0 is 1. What if the surface is vertical? Well, if the surface is vertical, then the plane doesn't really get in the way of the object going down the incline. And so it doesn't have, the surface doesn't have to push on it. It has no normal force. So that would be mg times the cosine of 90, which is 0. Okay, so it would be in free fall. So that, I think it's always good to look at these limiting situations just to see that it's working, that it doesn't just work for one particular value. All right, so that gives us the normal force. That's part of what we're asking for here, but the main thing kind of that we were asking for was acceleration down the plane. Okay, so here we can write then mg, this is the sum of the x forces, mg sine 30, and then there's nothing else because there's no friction in this problem, equals ma. Canceling out the masses, that just gives us a is equal to g sine theta in general, or in this case g sine 30, which should just be equal to g over 2. So as this thing slides down an inclined plane, it has a acceleration that's half the acceleration due to gravity at a 30-degree angle. Okay, so you might think, well, it should be half the acceleration due to gravity of 45-degree angle, because that's halfway to 90. Okay, and that might be logical, but trig functions aren't linear. Okay? And so a sine function doesn't work the same way as a straight line function. And so half the angle doesn't mean half of the sine theta is half of its maximum value. Okay, and so that's our general description then for an acceleration due to gravity down an incline is equal to g times the sine of the angle of inclination. Okay, so if the angle is 90, then this would be 1. The acceleration would be the acceleration due to gravity. But if theta is 0, then this would be 0 because it's just sitting on a horizontal level surface. So that one also works out. So once we have that established, now we can add friction. So I'm going to ask then to find the acceleration on the plane if the coefficient of kinetic friction is equal to 0.5, which has been the number that I've been using in some of these problems previously. So what I'm going to need to do to my free body diagram is add one more force to it now. That's going to be this force here, which is mu k times the normal force. And so now I think you can see why it was that I calculated the normal force in that previous problem. It was so that you can then figure out the friction force, and so therefore the acceleration due to gravity in this more complicated problem. Okay, so that normal force didn't help us until we had friction. We had enough information to get the acceleration, but now we don't. And so we can do now with friction, the vertical equations are still the same. So we can say that F normal is still equal to mg cosine theta, and our sum of x forces is going to be mg sine theta minus mu k times the normal force, which is mg cosine theta. So remember that this is the normal force expression that we got from the sum of the y forces. Okay, so that still needs to be done there. And then the sum of those two has to equal mass times acceleration. Okay, so we can then solve this for the acceleration by just canceling out the masses. Okay, so what that's going to give us then is the acceleration is equal to g sine 30 in this case minus mu k g cosine 30. And notice here that because the masses cancel out, what this means is that the problem does not depend on the mass. It means that as long as the coefficient of friction stays the same, this would be the same acceleration for really big mass or for really small mass. Okay? Because the mass, if it doesn't enter into the equation, means the result is independent of the mass. And so that's what happens. Anytime a physical quantity cancels out of one of these equations, it means that the result does not depend on that quantity. Okay, and so it's kind of the same reason that the acceleration due to gravity in free fall doesn't depend on the mass either. There's more inertia, even though there's more force with a bigger mass. And so that happens on an inclined plane, or it happens with vertical free fall as well. Okay, so let's plug in the numbers. Here we have 10 times the sine of 30, which is 1/2, minus mu k, that's 0.5, times 10, times mu k g cosine 30, that's going to be 0.866 for the cosine of 30. So that gives me 5 minus 5 times 0.866. Okay. And so we see then that it's slowed down significantly by something that has that kind of a coefficient of friction. And the result then is 0.67 meters per second squared. Okay, so that's a pretty high coefficient of friction. And so that slows it down considerably, because without that friction force, it would have been moving 5 meters per second squared. That here, only 0.67 meters per second squared. And so get this up to a 30-degree angle, and then we start this thing moving. It is accelerating a little bit, but it's nothing like the acceleration due to gravity if I were just dropping this thing. Okay, and so see that is somewhat reasonable just in terms of what we are doing here. If we assume that that calculator on the wooden surface had a coefficient kinetic friction of about 0.5.